All right, welcome back. We're going to move on to calculating a value that will help us determine the presence and the strength of our linear correlation. And that thing is called the linear correlation coefficient. It has the symbol lowercase r when we are discussing sample data, which we almost always are. And while we're not going to dwell on this formula too much, do not be afraid. You are never going to need to use this formula. StatCrunch is going to calculate this value for us. I think it's actually really important for us to take a look at this formula to help us understand how this linear correlation coefficient takes on the values that it does and how that relates back to the characteristics of our correlation. So I'd like to go ahead and take a look at this part of the formula. So let's sort of dissect that for just a moment. So let's start with the top, x minus x bar. Well, let's remember that x is our piece of data, x bar is the mean, and subtraction calculates distance between two things for us. So this is finding us the distance between or from our data point which is x, to the mean, which is x bar. All right, so we've got the distance between, the distance from our data point to the mean. Then we're going to divide by the standard deviation of the x values. Notice here that there is an almost identical calculation, but using y values instead. So actually for this r value, we're thinking about the x coordinates and the y coordinates in these ordered pairs separately. So what we're doing here for the x's, we would then also do for the y's. So this distance then is being divided by the size of the standard deviation of the x values here, since we're dealing with the x values right now. And so what this tells us, okay, so for instance, let's say the distance from the data point to the mean happened to be 6, and the size of the standard deviation is 2. This would come out to be 3. What does that 3 tell us? Well, it tells us that we are 3 standard deviations away from the mean. That's how far our point is from the mean, right? We're 3 2s to get a total distance of 6. This is also going to give us direction, right? So this is going to tell us the number of standard deviations above if this value comes out positive, or below if this value comes out negative, the mean. Okay, so if x minus x bar was 6, it means our piece of data is 6 units above the mean. Divide by the size of the standard deviation 2. We come up with 3, which tells us this piece of data is 3 standard deviations above the mean because it came out positive. So this calculation actually is something very specific. This formula is the formula for something called a z-score. And so this definition right here, number of standard deviations above or below the mean, is exactly what a z-score is. So we're finding in this formula the z-score for the x-coordinate times the z-score for the y-coordinate, and then we're adding all of those up. This is our capital Greek letter sigma that tells us to add things up. Then, much like in the standard deviation, we divide by the number of ordered points we have, minus 1, to better represent the correlation of the data set that our sample came from. So before we look at these particular values of our R value, I just want to bring this back to the picture that we've already looked at, okay, and see how these z-scores come into play. I wish I could keep this all together here, but let's see. So in the formula, we need, for every ordered pair, a z-score for the x and a z-score for the y. The z-score is relation to where you are to the mean, how many standard deviations away. So actually, let's go over to this data that I have here in StatCrunch, and let's find out what the mean is for each one of these data sets. So I'm going to do summary stats by column. I want to use both of the columns, and the only thing I want is the mean. So there are my means. Let's see. So for my x values, the mean of the initial drops is 155. Let's see, where is that? What is this point? This point has an initial drop of 161, so 155 would be a little bit back from that point. So I'm going to go over here on my picture. So maybe our x bar value of 155, and I'm just rounding 155.7, maybe it's about there. So let's give ourselves, I'm trying to make a vertical line, dividing line here, okay? So any point to the right of this line has an x coordinate, has an initial drop that is bigger than 155.7 feet. So the z-scores for all of those initial drops, the z-scores for all of those x coordinates will be positive. Any point to the left of this line has an initial drop, has an x coordinate that is less than the mean of 155.7. So all of those z-scores are going to come out negative. All right, well now let's think about all of our y coordinates. So the mean for the y values for the durations is 145.6. Let me see, what is this point? Oh, this point is exactly 145. So let's see, the mean would be just above that point. Let me get a different color here. So maybe about here is the mean of all the y coordinates, which is 145.6. And let me just carry that across. Okay, so now all of the ordered pairs that are above this line are going to have a z-score for their y coordinate that is positive, because all of those durations are larger than the mean of 145.6. And any point that is below this horizontal line will have a z-score for their y coordinate that is negative, because all of those durations, all of those y values are less than the mean of 145.6. Okay, so we have the sign of all these z-scores identified. And let's just go back and look at this formula for a minute. So notice that what happens is that we have to multiply those z-scores together. So let's think about what happens when we multiply these z-scores together in each of these 4 quadrants. So we're going to consider the 4 quadrants broken up by these mean lines, okay? So for these 3 points up here in this quadrant, the z-score for the x is positive times the z-score for the y is also positive, and positive times positive gives us positive. So all of those products are going to be positive for any ordered pair that shows up in this quadrant. Let's take a look over here. Well, now the z-score for the x coordinate is negative, right? It's to the left of this line, times the z-score for the y coordinate is positive because we're above the y mean line. Negative times positive is negative. Down in this quadrant, the z-score for the x is negative. We're to the left of the x bar line, times the z-score for the y is negative, and negative times negative is positive. Last quadrant here, z-score for the x is positive because I'm to the right of my mean line for the x's, times the z-score for the y's is negative because I'm below the mean line for the y's. Positive times negative is negative. So what I'm trying to get across to you here is, when is that R value going to come out positive? When is that R value going to come up negative? Okay, so let's look back down here for just a minute. So we find all these products for each ordered pair, the product of its z-scores, we add them up. Certainly n-1 is always going to be positive, so that's not really going to come into play when we're looking at sign. Okay, for points that are in this quadrant and this quadrant, all of those products are going to be positive. And notice that if we have a scatter plot showing positive correlation, these 2 quadrants is where we're going to find the majority of our ordered pairs. Notice that's what's happening here for our roller coaster, right? Lots of points down here, some points up here. There is this one point over here that's going to have a negative product of these z-scores. But by the time we add all these products together, we're overwhelmingly going to get a positive value. So when you have positive correlation, your points predominantly have these positive products of z-scores, and that makes your linear correlation positive. On the other hand, let me pick blue. If our scatter plot was displaying negative correlation, then it would be going down from left to right. All of our ordered pairs would be coming out predominantly in this coordinate, in this quadrant where our products are negative, or in this quadrant where our products are negative. So, negative correlation, most of the points are going to have negative products of z-scores. that is going to make that linear correlation coefficient come out negative. Which is really what I want you to understand here, is how the placement of those points in relation to the means leads to that correlation coefficient coming out positive or negative. And that's pretty much all we're going to say about this formula, okay? When you work this formula, it turns out that the R values must come out in the interval from -1 to +1. And I use the square brackets here because the R value could equal those endpoints. If the R value is exactly equal to +1, we say that we have perfect positive correlation. And that means that all of the dots are exactly on the same line with positive slope going up from left to right. If our R value is equal to -1, we say that we have perfect negative correlation, and all of our dots would be exactly on the same line with negative slope going down from left to right. If the R value was exactly equal to 0, then there is absolutely no evidence of a linear relationship. Which leaves, well, all that space in between, right? So when your R value is coming out anywhere here, that R value is positive, something greater than 0, then you have some evidence of a positive association. The closer you get to +1, the stronger that positive correlation is. The closer you get to 0, the weaker that positive correlation is. And then, of course, very similar thing true over here. If your R value is coming out anything less than 0, it's coming out negative, you have some evidence of negative association. The closer that R value gets to -1, the stronger that negative correlation is. The closer the R value gets to 0, the weaker that negative correlation, that negative association is. All right, let's take a look about the rest of these questions then. What does a negative R value tell us about the relationship? Well, that's saying that we have a negative association, a negative correlation. Correlation and association mean the same thing. Positive R value tells us that we have positive association. R value indicates a weak relationship. That would be close to 0. Although, what is close? It is still subjective. What R values of R indicate a stronger negative relationship? Well, that would have to be close to -1. What R values indicate a stronger positive relationship? That would be close to +1. But we're left close, close, close. How close is close? There are additional data analysis methods that you can use to quantify these things a little bit more, but we're not going to do that here in this intro to statistics class. So we're going to leave it with these two subjective things. We look at the scatter plot to get our subjective feeling about what we see, Then we calculate the linear correlation coefficient, and we put those two things together to come up with our best possible conclusion about linear correlation. So just to wrap this up, if we go back to that roller coaster data, which we still see on the right, what do we predict about that linear correlation coefficient R? Well, we thought that we had moderately strong positive correlation here, so we should come up with something close to +1. All right, let's see how that happens in StatCrunch. I'm just going to go ahead and close this window to give us some more room. So to do our calculations, we're generally starting with this stat drop-down menu. We're going to pick regression, which is a word we haven't talked about yet. We're going to address that in the next few modules in this unit. So regression is actually describing the relationship between our two data sets. Okay, so we pick regression and then we pick simple linear. Notice that StatCrunch can look for other relationships that will be described by a polynomial or by multiple linear relationships or other things. We're picking simple linear, and then this pop-up box, of course, looks very similar to others we've dealt with at this point. Our x variable is initial drop. Our y variable is duration. We're really not going to worry about anything else that's on this screen. Notice that in graphs, it's already highlighted to give us the fitted line plot. So we'll take a look at that in what comes up next. Click compute. And here we go. Now, don't get overwhelmed by this screen. We're actually only going to take a look at what happens in the top here. So the rest of this is part of that additional analysis that I told you could be done, but we're not addressing here in our class. So if we take a look at the top, confirm, independent variable, that's our x. We set that up as initial drop. And then our dependent variable is the y, so that is our duration. Sample size, we had 10 pieces of data, and here is the only thing we're interested in right now, our correlation coefficient. In OLI, frankly, everywhere else that I've always seen this, it's a lowercase r. Here in StatCrunch is the only place I have ever seen it as a capital R. But it spells out for us that it is the correlation coefficient. So hopefully we won't get confused. Let me just bring that over to our worksheet here. Maybe let's round off to 3 decimal places. So 0.90, let's see, 5, 6, so that will be 6, which completely confirms what we saw in that scatter plot. We thought that we saw a decently strong linear relationship, and now we have a correlation coefficient coming out reasonably close to +1. If you click this right arrow, you can not only see your scatter plot, but see the line that fits that data best, which is where we will be going in our next module. Next video, we will take a look at some more characteristics of our linear correlation coefficient value before moving on to that line of best fit in the next mod. This was a long one. Thanks for hanging in.